Hi everyone, I am Dr. Kiran, working as an assistant professor in the Department of Electronics and Communication Engineering, MLR Institute of Technology, Hyderabad, India. Today, our topic is biasing. So, let us see the overview of today's session. So, starting with introduction. So, we will discuss what is the need for biasing and effect of beta, that is amplification factor or gain factor, on Q point. What is DC load line, and we will discuss AC load line and stability factor and conclude with summary. So coming to introduction. So what is biasing? Biasing is the process of adding external voltage, particularly DC voltage to the diode. So we have a forward bias and reverse bias. Similar to this, it is a setting of DC operating conditions of an electronic component, say transistor, that process the time varying signals. So first, biasing is required to activate transistor, either BJT or FET or MOSFET. After that, then after applying biasing voltage, transistor is ready to do its work. That is, for example, amplification. So if the transistor is chosen for doing amplification, then first before applying AC input signal, we have to apply DC biasing signal. So it is essential to maintain proper operating point, Q point. Q point is also known as quiescent point. And compensation methods are used to get the stability of the Q point. You have to maintain proper operating point or quiescent point or Q point. Otherwise, your transistor may reach, actually transistor operated in 3 different regions. We know active region, cutoff region and saturation region, right? So, if transistor operated in active region, then it is utilized for amplification purpose. So, it must be operated in active region only. So, it should not go to cutoff region or saturation region. Otherwise, if you are not maintaining proper operating point, it may reach cutoff region or saturation region. That will be again another drawback. So, therefore, we need to maintain proper operating point. So, to maintain proper operating point, we need to bias the transistor. Proper biasing ensures that linear output, so distortion free output you will get for the class A amplifier. And proper biasing ensures desired clipping whenever required. So, in some applications, clipping is necessary. In such case, the particularly class B and class A amplifiers, clippings required. So, in such case, we can bias the circuit, then you can get the clipping option. For switching transistors, correct biasing prevents the transistor from being triggered by noise and ensures that transistor switches at the proper amplitude and time of the input signal. So, these are the introduction part. So, let us see in detail what is the need for biasing. To produce distortion free output in an amplifier circuit, the supply voltages and resistances in the circuit must be suitably chosen. That means Q point. So, for example, if you consider common emitter configuration, so this common configuration is mostly used for amplification purpose. So, in such case, we have to maintain proper supply voltages. That's VCE, IC is the Q point. VCE, IC. So, we must maintain these values. In order to maintain these values, we have to give some biasing. So, there must be established a DC voltage VCEQ. So, VCEQ means collector to emitter voltage quiescent values. ICQ means quiescent value, collector current quiescent value to operate the transistor in the active mode. These voltages and currents are called quiescent values that determine the transistor operating point Q point. The circuits used for getting the desired and proper operating point are known as biasing circuits. The collector current of the common emitter configuration can be given by IC equals to beta IB plus IC E naught, which can also be written as 1 plus beta into IC naught. So, here IC E naught means reverse saturation current. Here we can write IC naught is reverse saturation current, common reverse saturation current. Here the three variables HFE beta. So HFE, so this is for an AC analysis case. So HFE can also be represented with beta. Beta, IB and IC naught are found to increase with temperature. So this is the actually drawback of the transistor. So semiconducting materials will change their properties depending upon the temperature. So temperature changes the properties of semiconducting materials, though so they are temperature sensitive. So therefore beta gain changes, gain factor, base current changes and reverse saturation currents also changes. And we can say for every 10 degrees rise in temperature, IC naught doubles itself. Reverse saturation current doubles for every 10 degrees rise in temperature. When IC naught increases, IC also increases, because we can say IC is equals to 1 plus beta into IC naught. So if IC naught increases, IC also increases. So this causes power dissipation to increase and hence to make IC naught increases. Reverse saturation also increases, and this is undesirable. This process is cumulative and leads to thermal runaway. So the power dissipation will be more and then it causes thermal runaway. So you keep on in the loop, same loop. So it continuously to dissipate the power. So this is next. What is the effect of gain factor on Q point? So here let us draw the CE configuration. So this is your CE amplifier. Across this you will measure. This is emitter, base, collector. Here you are going to apply input voltage. This is RB and this is RC, collector current IC, base current IB, and here RE. However, here it is bypass capacitor is there. So this is common emitter configuration. So here, before applying this input signal, so we have here we are applying VCC, biasing voltage, and due to that the input voltage and input current are IB and VBE. This is VBE, and here you will have VCE, collector to emitter voltage. So here one more source of bias instability is to be considered due to variation of VBE with the temperature. So here the base emitter voltage changes with temperature. So which is just like a cut-in voltage, you can say cut-in voltage for a silicon and 0.2 volts for germanium at room temperature. As the temperature increases, the base emitter voltage decreases at the rate of 2.5 millivolt per centigrade for both silicon and germanium. The transfer characteristics curve shifts to the left at the rate of 2.5 millivolt per degree at constant IC. So by keeping collector current constant, if the transfer characteristics due to temperature effect shifts towards the left. So you can observe here. So this is the curve between VCE output curve characteristics of CE amplifier. VCE is the output voltage and IC is the output current. So if you draw the characteristics between these two, so these are the characteristics, and here you can, the transfer characteristics shifts to the left at the rate of 2.5 millivolt per degree centigrade. For increasing temperature and hence operating point shifts accordingly. So this is the operating point initially. Now because of temperature change, VB changes. So here the temperature, the Q-quiescent point changes its position and it reaches towards the saturation region. So this is another drawback. So to establish the operating point in the active region, we have to apply some compensation techniques that we will see later classes. And this is IC. So we have already know what is the output current IC is equals to beta IB plus IC naught. So this is the effect of beta on operating point Q point. Now DC load line, VCC and RC are fixed. By fixing VCC and RC, this is the circuit diagram. So we have fixed VCC and RC value. Then VCE and IC are dependent on base resistor, that is RB. So here if you apply KVL the output side, that is collector side here. If you apply KVL here, so what is the expression? VCC is equals to ICRC, this is ICRC plus VCE. So here we have VCE, right? So now, because here we have VCE, IC is the Q point, we know. VCE, IC is the Q point. The straight line. So this is the straight line A and B. The straight line AB of the endpoint. See here, AB is DC load line. Substitute. Now substitute VC is equal to 0. So in order to get the operating point, operating values. So that is, so this is VCE comma IC, right? So in order to get this is X and this is Y, right? So in order to have this X, we have to put Y is equal to 0. So therefore, in order to get IC, so we have to put VC is equal to 0. So on DC load line, so substitute VC is equal to 0. So if you substitute VC is equal to 0, so we get a VCC is equal to ICRC, and from this we can get a 0 comma VCC by RC is the IC. So on Y axis here, VCC is equals to ICRC plus 0. So because we kept VC is equal to 0. So therefore from this the output current IC is VCC by RC. So therefore that end, this point, at this point we can write V0 comma X0 and VCC, Y value is VCC by RC, right? Similarly, above we can substitute IC is equal to 0 in order to get the X value. So if IC equals to 0 in this case, then we will get VCC is exactly equal to the VCE. That means it is the maximum value, the biasing voltage. VCE is equals to exactly equal to VCC. So we can write this as VCC comma 0. So this we got 2 points A, B. So this is A and this is B, right? Now thus the DC load line AB can be drawn if the values of RC and VCC are known. So the Q point must be proper and stable, otherwise it may reach either cutoff region or saturation region. So Q point shifts its position due to. So what are the consequences of why Q point shifts? So we have already seen. So let us see one more reason. VCC and RC are fixed and VCE and IC are dependent on RB. So RB changes, because RB changes, IC also changes, because we know IB is equals to beta is equals to IC by IB, right? So this is common emitter. So output current is IC and input current is IB. So if RB changes, base resistor, so obviously IB changes. So IB changes means output current IC changes and beta also changes. So that leads to change in the Q point. Reverse saturation current IC naught, which doubles for every 10 degrees centigrade rise in temperature. So this is another effect. Base emitter voltage VBE, which decreases by 2.5 millivolt per degree centigrade. Transistor current gain beta, that is HFE, which increases with temperature. Beta varies or range that results in the variation of IC for a given IB. Hence, in the output characteristics, the spacing between the curves might increase to or decrease, which leads to the shifting of Q point. Just now we have seen shifting of here, shifting of Q point. Now let us see AC load line. What is AC load line? So before applying AC supply, so we have to apply DC biasing voltage VCC. So here after applying DC, so we have a VCE comma IC or Q point VCE Q comma, we have to maintain this ICQ quiescent values of VCE and IC. So this operating point is chosen under zero input signal, that means without applying any AC signal. Hence the AC load line should also pass through the operating point, this operating point. The effective AC load resistance. So if you consider here, the effective load resistance RAC is parallel combination of collector resistor and load resistor. So here RC is there and this is RL is there. So RC parallel with RL will be the resistance of the RAC. So the slope of the AC load line CQD. So here this is CQD, this line. Now the slope, what happened? Minus 1 by RAC. So initially it is VCC by RC. If you see the here, this is IC is equals to VCC by RC. Now here it is minus 1 by RC is the slope. So maximum VCE is given by VCEQ plus ICQ into RAC. So just like just now we have written, which locates the point D, that is this point. Similarly, maximum IC is ICQ plus VCQ. If you apply KVL, so we can write all this. So which locates the point C, OC, that means this one. Now by joining C and D, AC load line is constructed. Now as RC greater than RAC, collector resistance is more compared to AC resistance, because AC resistance is combination of RC and load resistor. So obviously parallel combination means it is reduced. So therefore the DC load line is less steep than AC load line. So if you observe this, this is the load line, AC load line is more steep. So DC load line is less steep. So that is the difference between AC load line and DC load line. So now another important parameter, that is stability factor, which represents the performance of operating point. You can say how much time the operating point is stable. So it is, stability factor is defined as the rate of change of collector current IC concerning the collector base leakage current IC0, or keeping both IB and current gain beta constant. So here S is equals to dou IC by dou IC0. So here IC means collector current. This is your collector current IC. So this is, let us say, NPN transistor. So IC, change in collector current by change in leakage current, that is dou IC0, or you can say reverse saturation current. This is IC. So we can also, so this is like a change in small current value. So small current values means you can write a differentiation. You can represent with differentiation. So that is DIC by DIC0 or delta IC by delta IC0. So when beta and IB are constants. So this is called stability factor. And we know that from this we can say IC, the output current IC can be represent beta IB plus ICE0 or 1 plus beta into IC0. Differentiate the above equation concerning, or by putting IC constant we get. So if you differentiate with respect to IC, so what happened? IC different DIC by DIC, DIC by DIC. So it will get 1. So 1 is equals to beta DIB by DIC plus 1 plus beta into DIC0 by DIC. So if you solve for this, so stability factor for this we get 1 plus beta by 1 minus DIB by DIC. So S must be small to reduce the thermal stability. So in order to maintain proper thermal operating point, and so if you change this S value, so if you change with S value means that means beta value changes, S value also changes, and also IBIC. So it depends on base current as well as beta value. So S must be stable or very less compared to these values. So in order to maintain or reduce the thermal stability. And one more important relation of stability factor is S dash and S double dash. Those are relation between IC and input voltage VBE. This is input voltage VBE. So that is output current IC. So S dash is defined as ratio of output current, collector current, change in collector current for the change in the input voltage VBE. Similarly, S double dash means change in the output current IC by change in the beta value, dou IC by dou IB, dou B, or delta IC by delta IB. So if base current changes or gain factor beta changes, stability factor changes. Stability factor changes means reduces, increases means that is the drawback. So operating point changes. So that leads to distortion in the amplified output. So that is about today's session. Today we have learned, so we have started with introduction to biasing. What is the biasing? Biasing is adding external voltages to the particular diode, or we have to maintain proper DC condition, DC values in order to change the time varying signals. And what is the need for biasing? So in order to maintain proper Q point, and then effect of beta. So VBE changes, IB changes, and correspondingly Q point also changes. So that is the effect of beta on biasing. And DC load line, AC load line we have discussed, and stability factor, which represents the stability time of the Q point. So the next topic probably will be biasing methods. We have different types of methods, and then followed by compensation methods. Thank you.